Okay, hello everyone, and welcome to this live stream where I will attempt a blind solve of a crackme challenge that was posted by a Twitter user named s4tan or Antonio Parata. So this is a blind solve of this challenge, which means I have not looked at this at all. I have no idea what this challenge is, except that it's a crackme. And well, with that, let's get into our setup. So you should be able to see my virtual machine and my terminal. And please let me know if if there's something wrong with the audio or video, and we will be starting shortly. So here is the GitHub page with the challenge that was posted. So we have this thing, this repository with the challenge called Satanic Code. And yeah, so it's binary, contains some tricks with some revivals from old school era. And Tony is saying that we'll publish the source code later. And the goals is to first find one valid ID and license pair, and then write a license generator. So we have a release here with the files. So we'll go ahead and download this and just move it into our directory here. Okay, so with this we are almost ready to go. Let's open up VS Code to prepare to take some notes and start writing some scripts. So we'll have like a notes.txt. Let me increase the font size a little bit. Please let me know if the text is readable or not, or if I should increase it even further. I'm just gonna, before I really get into the solving, I'm just gonna wait for a few more moments. I'm just stalling a little bit to make sure that people who want to catch the stream are online. But I can basically just quickly again explain what we're going to do. So we have this challenge, which I've just downloaded, and I'm going to attempt to solve this challenge. I have never looked at it before. I have no idea what it is, apart from what has been given here in the instructions. And this also means that the point of this thing is not necessarily the solution itself. Because like if that would have been the point, I could have just solved this off stream and then just done like a run through of like how you solve this. So this is more about the process, like how do I approach this, how can you reach the solution. So this means that if you have knowledge of this challenge, like if you have solved it before or worked on it or something, please do not post in the chat about this. So feel free to post other like questions or comments about like tools or methods or ideas like that. But please do not like spoil the challenge itself, because I will try to like read the chat and like answer questions, and maybe we can have some kind of discussion around this. So yeah, I just hope everyone is clear on that. And also, it might be the case that this is a super difficult challenge, and I don't really have like a strict time limit, but I will go at this for a while, and I don't know, maybe an hour or two or And if I haven't solved it by then, I may or may not continue or just wrap this up. So we'll see how far we get with this. And with that, I think, well, let's start. So let's start by just using files. So this is a PE file, a Windows executable, a 32-bit executable. So there's a suggestion like, please use Ghidra. I'm broke, can't afford IDA. Unfortunately, I'm not very good with Ghidra. I could, I guess, use Binary Ninja for this, which is, I mean, it's not free, but they have the free cloud version, so you can go pretty far. And also, it's like way cheaper than an IDA license. But yeah, I'm gonna actually gonna go with IDA in this case anyway, because that's what I'm absolutely the most comfortable with, and yeah, I think it's much better than Ghidra for most situations. So let's open this up. Okay. So we have here some kind of start function. Let's see if this decompiles to anything reasonable. Already we see, if we try to decompile this, that it looks a little bit funky. So there's something here with like exceptions and some like read flags and write flags. So, oh yeah, sorry, someone said, can you increase the font size? Absolutely. Let's see, we can increase this like this. Is this better? Unfortunately, I don't really know how to like increase the font of everything, but I guess the main thing is like the actual code and disassembly here. But if we go back to the disassembly here, we see that we have some kind of entry here, reference to a string, like please enter your ID, and then calling some function. And then also please enter your license key and calling some function. So it's a fairly good guess that this is some kind of print function. And we can also see here that we also call some function here and some function here, which it would be fair to guess that these are responsible for like reading the ID and reading the license key. And then assuming this all goes well, it seems that we go into here where it says like license validation in process. Okay, first of all, let's just rename this to like print 1. And then yeah, some stuff is happening here, and in the end, so there are a few functions being called, and then we get down to either here the inserted license is not valid, or something else happening. So probably, you know, the license is valid and something will happen. So that's already, we have some kind of like very high level structure here. Oh, we also have some function call here before it even starts the reading of the input. So that's also going to be interesting. So let's keep it simple for now and check this function here, which we think will read our ID. So let's see if we can get like a reasonable decompilation out of this. And this in itself calls a function here, which calls read console A. So yeah, there is some kind of input reading going on here. And then I guess this is, yeah, so here we're looking for a line feed. And so there's maybe some copying or trimming or something going on here. Not entirely sure yet. So it was a question like, what button do you press to get the code? Yeah, so I'm using IDA with the decompiler. So you can use the tab button to switch. So this is the disassembly view, and you can switch with tab to get the hex-race decompilation, which is, I mean, it's extremely good, but there were also indications that, you know, there's some like that this is written in assembly, and there's some tricks going on. So in those cases, the decompilation might not always be very good, and sometimes it might even be misleading. So I will be using both the disassembly and like the decompilation while going through this to be sure, because the decompiler might completely misunderstand what's going on in the code. So we're back here at the top level. So I think if we yes, so up here we can see these calls to so this variable here will probably be the license ID, and then this variable will probably hold the license key. So that's something, and these are actually pointers to other stack variables. So, and here again we ask for the license key, and is this where we were checking that something was not erroring out? Let's see where it is. Okay, so label 4 was this not valid. Okay, so we can rename this to license invalid, and this is the like result code. So let's actually rename these functions then. So we call this one like read license ID, and this one read license key. And we can just call this like the destination, and I would assume this would be the length of the buffer. Let's check. This is passed into this function here. And here we see that they do a memset on the buffer with this as a length argument. So if we follow that backwards up, we see that this is this argument, so that is the length of the buffer, and it goes up all the way here. So yes, it makes sense that this is the length of this buffer. So actually this means that we could probably so these are pointers to these regions, which should then be 95 bytes buffer. So we could actually set this type here, and this one as well to 95 characters long. Okay, and it automatically claims that they are 96 bytes long, because there is some, I mean, either they are actually 96 or there's just 1 byte of padding here, but not that big of a deal. So let's actually update these and call them license ID pointer and license key pointer, and then we call this one license ID and license key. Okay. Yeah, that's something. Actually, let's look at this like startup function or something that's going on here before the reading starts. What happens in here? Okay, so here we have a call to set console, get standard handle and get console mode. So these are like Windows API functions. So I don't know from the top of my head exactly what these are doing. So just let's Google this and go to the Microsoft documentation, which is most of the time excellent, by the way. So it says, we can actually zoom in a little bit, retrieves a handle to the specified standard device, standard input, standard output, standard error. Okay. And we are calling this with let's see what the assigned values. Yes, so we should just change the type here to a number. Oh, we should actually switch here. Operand type number. I think. Oh wait, how do we do this? Yes, like this. Or it didn't propagate. Okay, anyway, this is -10, which is the standard input handle. Actually, I think we should be able to do this. And yes, excellent. So this is, we told IDA this is one of the enums, and it has like a huge library of all like the Windows APIs and enums and stuff. So it could identify that this was the standard input handle. So we can call this standard in. And then it calls set console mode on standard in with this argument A0 or 160. So let's just look that up as well. Okay, so first argument is handle, and then we have the mode. And okay, so this is like a flag thing. So A0 would be that would be, so that's 10, so that would be okay. So that's 2 bits set, which would be 8 and 2 would, I guess. So it would be insert mode and now I'm a bit confused. It should be if we take yeah, exactly. So it should be 2 flags set on this, which should be 8 and 0 and 2 0, but it doesn't seem like there is a 8 0, which makes me a little bit confused. Okay. anyway, it's something about how the input works. So maybe not a huge deal at the moment, but we can just call this set standard in mode. Maybe we'll have to come back to that later, but for now let's not get like bogged down with details and just keep up some momentum here. And let's look at the disassembly again. Oh, so here we start doing stuff with input, I guess. Let's see actually, where are those variables referenced? Yes, so in this function call, so it just referenced some location. Okay, yeah, so if we look here, or we can actually go back to the compilation here, we see that it's making a call to this location, but IDA has not been able to identify this as a function. And if we look here at the entry here and treat this as code, this looks very strange. Like if we interpret these bytes here as code, this is quite nonsensical. It's like we're ORing into some address referenced relative to the EBX register, and then we're adding to the EAX register. It's like, this is probably not correct. So I guess that what we're dealing with here is some kind of a packer. So the idea here is that this would be the license verification, verify license, but probably this, let's see, somewhere here between reading the license and like in one of these functions or in all of these functions, we have some kind of like code manipulation going on. Or this is also, if they're actually doing something with the, okay, they're doing something with the exception handlers or something. So yeah, we're gonna have to look at what's going on here. And then hopefully afterwards, what is this variable? Is this used? We don't really know. And this is, we also don't really know. So let's start looking at this function, which is the first one we haven't really looked at all. And this one is called, it's like the first thing that's called after we have successfully read the input. So we go into here, and here we do a call to virtual protect. So probably here we're changing the permissions of a memory region. So yeah, there's a question like, what do you mean by blind solving? Yeah, so what I mean by blind solving is that I have not looked at this challenge at all before. Like I'm going in blind. So I don't know anything about this challenge. I don't know how to solve it. I haven't opened it before this stream. So you really get to see like the whole process and my thinking about this. And so far, yes, I've been only looking at this statically. But we will also get to some dynamic analysis, I'm pretty sure, as well. But so far, we're just getting some kind of overview of this. So here we can I'll just call this function like called virtual protect. So we're reading some memory region here, and then we're calling virtual protect. The parameters here are, first we have the address, and then there's a size argument, and then we have the new protections. And I don't have these memorized, but I'm gonna assume that this is setting these to like writable or something, but let's look that up. And this is just the old protect, which I guess we don't really care about. And then what happens afterwards? Let's change these to hex values. You can see there's some kind of constants going on. So getting the same pointer here. And then what is this doing? It looks like it's just shifting stuff one element at a time. And yeah, some kind of like modification of this memory. So I still don't know about the details here, but I'm just gonna call this like modify memory 1. And then we have another function here, which looks a bit interesting. Here is a reference to the name, the satanic code SAT plus. So maybe this is some kind of SAT or SMT problem involved here, or it's just SAT for like satanic, or I don't know. And there's some kind of magic value here. And then, here, let's see, if I'm not mistaken, this could be this thing where you switch between some modes. Like this looks like the same thing you do when you switch between 32 and 64-bit mode, but let's not get ahead of ourselves here. So we'll see what happens. Interesting function anyway, and it's actually you saw that the decompiler incorrectly thought that this was taking an argument, but then when we looked at it again and did some reanalysis, it no longer thinks that this function is taking any kind of argument. And then we're just setting up to call this verify license function. So let's again go back to the virtual protect thing here and actually look it up to make sure that my guess is correct. So the new protect memory protection constants, page execute read write. Yes, so this is just that we're setting this up to be executable, readable, and writable. So this is what happened. This is what allows us, if this, assuming this memory was not writable in the first place, or maybe it was not executable, this allows us to now modify the memory. So now let's actually check what this is, because I'm not quite familiar with this. So this NT current PEB is getting the guess it's getting the address of so this will get some like information about the process that's running. Actually, what is this? Yeah, so PEB is process environment block, I guess that's the name. And this pointer is pointing specifically to, I would assume this is getting like the current segment, but I would like to get a more definite. We could also just run it and check what it's pointing to. Handle. Anatomy of the process environment block. That looks kind of good. So this thing is referenced here, but yeah. Should probably maybe just run it in a debugger to verify this, but it could be that it's just getting the a reference to the current like the whole program and just making the whole thing executable. Sorry, writable. And then let's look at this modification here. So here it will just step through. Oh, sorry, I read it wrong when I talked about this previously. This is just it's just stepping the pointer forward until it finds this value, and then it checks that. Okay, so first it will go into this inner loop and loop until it finds this value, and then it will check that the following 3 values are these. So basically we are looking for a sequence of these 4 32-bit values in the memory. And when it has managed to do this, it will store this location in this global variable. And then here it actually stores the starting value. So this is like original memory pointer. And then it does this searching again, but now it's looking for this sequence of 4 values. And it stores this pointer in this result. So this could be that it's looking for like the beginning and the end of something. So just call this like start pointer and end pointer. Now this could of course be completely wrong, but it would make sense if it's just like looking to find these 2 locations in memory. Also, we're gonna change this because this doesn't actually return anything. So it looks much more clean here. And actually the same thing here. Just remove that return statement. So this is actually not at all modify memory. This is like find markers, maybe. That's a good name. Okay, so then, yeah, then we have this interesting function that we talked about. But before we do that, let's actually just write some code actually to find these markers ourselves. So create a Python script and we will read this executable file. And we are looking for these 4 magic values. And then we are also looking for these 4 magic values. So yeah, so there was a question about what shortcuts I used. Yeah, so this is actually something very common I do. I can just walk you through what I did here. Some nice VS Code trick. So we want to like extract these 4 values from a code block like this. So first I just search, like I look for something common of all these constants, which would be the 0x. So I mark the 0x on the first one. Then I think I have like the default VS Code mapping, so you might have a different keyboard mapping or whatever, but there's like select duplicate or select more of this. So there's like Control D to just select another occurrence of this, and then just using like Shift Alt right to like select the whole word. So now we have 4 markers, so 4 selections of all of these. I copy all of those, select everything, delete it, and paste back the 4 segments I have selected. Then I select all the text again, use like Alt-Shift-I to split the markers, this selection into 4 markers, 1 per line. Then I add a comma, a space, and then delete to delete the new line. And then just Control A and just copy it into my Python script. So that's a nice way to just quickly extract some values from a block of text like this. So let's see. We just read the whole file, and then so this was actually stepping 1 byte at a time, so we'll have to do this as well. So like 4 offset in range. So we step 1 step at a time, and we look at this candidate, which would be, so we want to take 4 32-bit values, so that's 4 times 4 bytes. So we want to get 16 bytes from the current offset. So from the offset to offset plus 16. And then we want to unpack this into 4 32-bit values. And then if this list of candidate values is equal to the magic start, then we store this offset, and we can actually do both of them in one swoop. So if those values are equal to the list of magic, the other values, we do offset end, and we store the value, we can do, whoops. So, okay, we're just printing that. Okay, so we should be able to just run this. Something went wrong. Oh, right. When this gets towards the end, then this will no longer be 16 bytes. So we should actually not go all the way. Okay, it didn't find these values, so that's a bit worrying. Oh no, actually I think this is because, okay, so yeah, no, so this is a bit a small subtle thing. I think this is what's happening. Notice here how I have made these lists, but unpack returns a tuple. So I'm pretty sure that this is the thing. If we actually print out and then just break on the first one. Yes, so we're trying to compare two different types. Will not work. So the easiest thing is to just change these to tuples, and now it works. You need to be careful with your types when you're doing comparisons like that. And actually, how do I, let's see, so I'm using these new f strings in Python, but how can I do like hex format with those? Python f string hex. Yeah, no, let's just go to the old style formatting. Okay, so now we have two nice addresses. With some nice prefix here. So this is the offset in the file where this occurs, which is not necessarily the same thing as the virtual address when this is loaded into memory. So someone said, looks like you can use varname :02. That sounds very nice. I will actually, let's look at this because we are all here to learn. So it's, I would do like 08x, or I could do this. Right, that works. Excellent. Then let's do this. Let's move on to the future. Use these f strings properly. Thank you, Salki. Yes, as I said, so these are the offsets in the file on disk, which is not necessarily the same thing as the virtual address they will have in memory. But we can look here. It's very difficult to see, I think, for you, but here in IDA, when you look at it like this, you see the virtual address, but also down here you can see the offset in the file. So we can go to bb9, which Oh, so here we have like a whole chunk of memory. So BB9 would be here. So we call this the start marker. And then I would guess that this is then the other one is like at the end of this big block. Let's go up a little bit again. The other one was like 50DE, which is, all right, we get, so this one points to 51. Yeah, so it's like in the, oh yeah, here we can see the values. Like if we undefine like this, and then we go forward a bit to 50DE, which is exactly here. Here we have 50DE. So here you have those 4 values: Cafe Babe, Dead Code, and then something else. Code Chaos, Ice Baby. Yes, exactly. So this is the end marker thing. Okay, so we know that we have this chunk of data in the beginning of the file, which this one is looking for. And it's storing them in these 2 global variables. And then we get into this thing here, which was this strange jump thing. So as I said, this really looks like this thing where you switch retf. Let's just Google that to refresh my memory. A x86 retf, and then yeah, so you can already see that I have actually already read about this at some other time. So yeah, this is basically a way to change the architecture mid execution. So basically what we're doing here is that first we push this hex 33 value on the stack, and then we do just like a dummy call. So we're just making a call to here. I think this is just like calling to the next thing, which is effectively what this is doing is just pushing the current address to the stack. And then it's basically incrementing this by 5, which would, so what we're pushing on the stack is this address ending in 53. And then we're incrementing this by 5, making it 58, pointing here. So now we have on the stack, on the top of the stack, we have this address. And then below that, we have this hex 33 value. So when you do this return var, it will pop this address into the instruction pointer, and then this one will be popped into like the segment register or something like this, the CS register. And you can see here from this write-up, like if it's 33, we switch to 64-bit mode. And if it's 23, it's sorry, if it's 33, 33, it's 64-bit mode, and if it's 23, it's 32-bit mode. So basically, this will be executed as 64-bit code, which is now a little bit annoying because I can't just say that this is like 64-bit code. What we could do is just like, it's a little bit ugly, but we could just open, I guess, no, wait, cancel. Since it's just like such a small piece of code, we could probably just open this in Binary Ninja, so I can show that a little bit. Open this exe file, and we go to this address, and so that you can create a segment for 64-bit. Yes, but not in 32-bit either, right? Or can I? No, then I would have to like open this up again in 64-bit IDA. Yeah, well, maybe we'll do that, but let's just see here. So we have this 5E58, which is here, and can we like undefined current function, and then make function x86-64 Windows. Okay, so this is what the code is doing. We fetch some values, and then it's doing some XORing. And then here, I'm assuming it's just switching back to 32-bit mode again. So first of all, just before we figure out what this part is actually doing, let's just check the control flow here. So again, it's doing like a dummy call, and then changing the adding this value to the stack, and then it's adding yes, I can increase the font size a little bit in Binary Ninja, I think. Settings, probably. Font size. Let's go to this. How do I? Okay, is this better? Whoa. So what this is doing now then is it's just executing this code as 64-bit code, then switching back to 32-bit mode and jumping to this address. So look at this address in IDA again, and this is this ends with 9A, so this would be down here. So we can just define this as like 64-bit so we don't properly disassemble this here. We just say this is actually 64-bit code, which corresponds to just this block here, and then it's jumping back into this part here, where it's just going to return again. So this is all good. So this is gonna do something. We don't know about exactly what it's doing yet. But then, whoa, sorry. It will call this verify license, which is this thing here, which is still messed up. So probably what's happening, let's see what's actually happening inside of here. This thing, so we're getting so let's see, the start of the function is at 43. So we have right, so we're moving a this value into this ESI register, and then we switch to the 64-bit mode, where this is XORed with this RBX value here, which here it's doing a conditional move. So it's testing yeah, so basically it's fetching this. So this is I think this is where this PEB block is. It's fetching this and like dereferencing it all the way until, so this is like a hierarchy of pointers which is then dereferenced into this RAX. It tests this, and then it will create these two constants, and then it will conditionally move, like overwrite one of the constants with the other, and then use that to XOR. So basically, depending on the value of this byte that we fetch from the PEB, it will XOR this RSI with either this bad code or Cafe Babe. And that's what the function. So what is this then? This is this coming from this global variable at address which ends with B6. So this is, did we look at that yet? Whoa. What did I say? B6. All right, this is this special value that we don't know yet what this is for. Actually, do we see any references to this? Yes, this is here. Okay. And then afterwards, it's moved back into this location. And that's it. So let me just call this like, I don't know, magic 1. So then what is this this value that is actually checking? And also, where is this value even? Do we see anywhere if it's used anywhere? Okay. Doesn't seem like it, but of course this could be in this like modified code or something that we don't know about yet. This is also something we should look up, I guess. Read e-flags, write e-flags, which I'm also not like super familiar with, or like from the top of my head. First of all, we could actually just look at this this constant that we had here, which is at offset. This is hard to read, but it says 58B6. So let's just go back here and what did I say? 58B6, 58B6, and I just want to print and see what that looks like. So we fetch this 32-bit value. And then we consider both these alternatives. I just want to see if it like spells out something interesting or whatever. Yeah, so this could be interesting, I guess, but I'm not sure. We'll just leave it for now. But basically, so far we haven't found anything that actually like modifies or unpacks or something this code. So now we will have to look at what's going on here. And first of all, there is a function pointer here, which we could look at. Let's convert these to hex values. Some kind of data structure being manipulated. Oh, here we see reference to these start and end pointers. And this could be like an exception handler. So it could be that they are like setting this up. There is a technique where you have like a block of like encrypted or invalid code or something, and you set up like an exception handler and you call into this code and it will break, and then the exception handler will like unpack the code and like return control to it and so on. So it could be something like this going on here, but I mean, we don't know that yet, but that could be the case. So we're definitely gonna Google these constants here and see if they correspond to some type of error code and so on. But first we're just gonna check these things. So we have this thing is, it looks like it's handling like two different cases, like this error code or something is handled here, and this code is handled here, and then we have like a default case here, and then it's something. So okay, let's just call this like handler1. We don't know what this is yet. So I'm suspecting the decompilation here is misleading. So let's see what happens here. Stack pointer. It's also setting some kind of flag here. It's setting it to 1 here and then resetting it again. Where is this used? Okay, it's used inside of this handler, so that's also interesting. So let's search for this. I think we have some kind of this reverse engineering, malware, dynamic analysis. Oh, I accidentally started another instance of Binary Ninja. Yeah, so installs an exception handler. That's okay, so here, install a structured exception handler. I think this is the abbreviation. So what you do is you push the offset to the handler, push pointer to the old exception record, and then update the exception list. I think that matches what we're seeing here, right? Yes, absolutely. So here we are installing, this is a structured exception handler, and then some stuff going on here, but then we call this. So essentially this is misleading here because these two arguments here are not actually arguments, like, because it can't really, the decompiler can't properly represent this exception handler thing. So it thinks that since we're pushing these objects to the stack, they are arguments to this function, but that's simply not the case. So I would say that this function is, or like this is actually a function pointer. So this would look something like this, I think. Of course, I got the syntax wrong. Is it like this? Yes, and then we also do set call type. So here we get rid of these two extra arguments. Nope. Oh, maybe I should have. We want to get rid of these arguments. Oh, right. This is the, okay. So like this then, I guess. Right. Yes. Yes, now it looks good. And then we can actually, I guess, do this. Okay. Looks much better. So this is the result of, I guess, maybe this is actually not the verify license. Maybe this is actually the verification. But anyway, we're going to call it verify for now. Because it might be that you have all of these three. Okay, wow, there's a lot of other stuff going on here as well. Anyway, so this is probably not purely verify license, but we'll call it this for now. Okay, and this function was like decrypt magic 1, doing this like 32 and 64-bit trickery. So now let's look at this handler, and actually let's get some, let's keep these slides but close these other things, and then also search for like SEH and this code thing. Or maybe just search for like SEH handler, structured exception handling. I expect that we don't really, like, there will be some abstractions on top of this which will actually hide so this is probably like the I'll call it like error code or something, and these are things probably pointing to privilege instruction. Exception code. So what is this doing when not exactly sure. Let's search for the other one. Debug exception. That could make sense. Not sure about this other one though. So what happens in that case? Ooh, so this is some kind of structure. And what is this? This is some kind of table. Is it specifically like 16 elements? Because we're fetching some kind of record in the structure and then dereferencing it as a, no, sorry, that could be up to 256 records. So we don't know that. But we have at least 21 elements here which look kind of similar. And then here we have, yeah, no, this is probably also part of this list. So like 22 elements. So just call this like table 1 for now. And what do we do with this? Okay, so we're replacing something. So we have some kind of structure. We're using some entry in this structure to look up something in this table, and then we're storing it back in the structure. So, okay, we don't really know what that is yet. And then what do we do here? We copy 15 bytes to this pointer from here. 15 bytes. And where is this referenced? It's referenced in this function, which is referenced from here. Okay, so it's only used in here. Interesting. So we would like to, we need to figure out what these like arguments are and what kind of structure this is, but we have some kind of like global variable here, some global array, which we copy stuff from. And then what happens, we fetch something from the same structure here. And if it's within this sequence of start and end thing, we call this function where we copy stuff again to this temporary variable. And then, oh, okay. Here is some interesting stuff going on. Looks almost like some kind of encryption or decryption function, possibly. Okay, it looks a bit messy, but yeah, I mean, this is definitely like core to how this execution works. So we should look this up. This how these handlers work. See if we can find some simple explanation of what the arguments to the actual handler looks like. Just exception handlers. So the problem with this in the like documentation is that I guess that like the way you write this code is not like actually really what it gets compiled to. There's like some internal details hidden there, I think. So yeah, because these things only have like one argument, but we're looking for something with like 3 arguments. Whoa. Exception handler, exception record. Could this be do we have these yes, okay, so this looks realistic. So this is an exception record, and then the other things would be establisher frame and context record. So this doesn't seem to be used, but then you have this context record, which is probably very much relevant. Luckily, IDA has all these types. Okay, so now this looks much more readable. Let's just get this. So actually get rid of the return. And this is the instruction pointer. This is context. Now this is starting to look very nice. So we have this context and we get the stack pointer. And it's looking up things at the where the instruction pointer is located. And then it sets like a new stack pointer and like a new instruction pointer. So this is like update EI update the instruction pointer and the stack pointer. And I'm just going to summarize this as soon as we've looked at this. And this, not quite sure what it's doing. And here we're doing something with the instruction pointer. Okay, so let's just like back up a little bit. So basically what's happening is that when we set up this execution, this exception handler. Actually, that's probably what those flags are doing as well. So if we actually back up a little bit more, we have these flags here. I wonder if this is what causes exceptions to be thrown for stuff. But anyway, we set up this exception handler. And then when we get an exception, if the exception code is this, I wonder if, do we have a, no, we don't have a good thing for that. But anyway, if we get this, then it will look at the context record, which contains these things like the stack pointer and like the registers, and basically. So it will take the current stack pointer -4, and it will update the stack pointer with this. So it basically will decrement the stack pointer with 4. It will take it will look at the current instruction pointer, look at the next byte, and use this to look up this value, which will be the new instruction pointer. And then also it will take it will store the current instruction pointer +2 on top of the stack. So this is like, it's basically redirecting. It's redirecting a call somehow. So it looks like that's what's happening. It's yeah. But we'll see. That will probably be clear what it's used for when we when you see it in context. And then what happens is that it will take 15 bytes from this like global array, which we don't know what it is, and copy it to this pointer, and then it will zero out the pointer. Okay, but we don't know what's in this array, and we don't know what this pointer is pointing to, so that's not quite useful yet. And then finally it will take the current instruction pointer, and if that instruction pointer is within these chunk that we found previously, we will call this function, which will take the function pointer. Okay, we'll copy the code there, or like it will copy the next 15 bytes into this temporary buffer, and then it will copy another 40 bytes of stuff into this array, and then it will get the offset of, so we already know that we are inside, let's say this is the instruction pointer. So it will take the offset within this block, divide it by 10. Actually, I'm gonna remove the return type here again to make the code more clear. Oh no, okay, so it's just taking the offset modulo 10 and what is it doing? Okay, it's rounding it to, it's running it down to a 10 and then looping this thing, which is doing something. Okay. Is it, what is this? This is a pointer to some, oh, it goes even deeper. Now this is a little bit annoying. Okay, so this is some kind of is this like some kind of random number generator possibly, or a bit unsure. It's indexing into this. How big is this list? Okay, maybe this is, okay, this is huge. Okay. Okay, don't really know what that's doing. remove the return type here to get a more clean. Yeah, so basically it is modifying the code or something in this where the instruction pointer is pointing. Okay, so let's see here. And the other case is if there is a so this is kind of a bit like inverted here. So basically, if the exception code is this, then this part will be executed. Otherwise, we will just return here. I think so. This is kind of like the default case. And so if we get this thing here, we just do these two steps are common between the two cases, but we don't do this thing here where we like update the instruction pointer and the stack pointer. So yeah, that's interesting. Maybe it's like time to start to do some dynamic analysis on this. I think so that we can get like a sense of what's going on here. But first I just want to check, like, if we were to call here, yeah, no, let's do this. So let's see, start my Windows virtual machine to be able to debug this. So should be starting up. In the meantime, like, does anyone have any questions or comments so far with what we're doing? Has everything been clear so far? Are you still awake? Just falling asleep from my ramblings? Okay, so here we have hello Jacob, my old colleague. Nice to see you too. So we're gonna copy this file over to this shared directory I have between the two virtual machines. So we have this here. So we could actually start by, I guess I'm just gonna assume that this is not too malicious and ruin my virtual machine. So we can try by just running this. Okay, so apparently Windows Defender does not like this program. Therefore we do this, we just disable. Okay, so we can run the program and it does what we we already saw it was gonna do. It will take some input, like an ID and a license key, do some validation, and then it said it's not valid. Yes, I know I have turned off this. So let's debug this. So we're gonna use x64 debugger, and yes, here is the entry point. I should probably increase the font size here. Can I do like this? No. Okay, do I have to like adjust all of these? Oh, okay, setting this requires, okay, yeah. So could I do just this and then restart? Okay. Yeah, okay, it changed everything except the important stuff. Okay. Actually, for my own sanity, I'm gonna switch that part back to small and then actually just increase the font size in like the disassembly and the hex dump. So just do all of these. Yeah, that's okay. So we jump to the entry point. Like this. So let's see. I can switch back and forth between the VMs and it will show fine, right? Let's just gonna check that. Yes, okay, good. So now we probably want to find like a good place to set a breakpoint, which would probably be here, right, when doing this license verification thing. So, no. Where's the... Yeah, okay. You go here, we can set the breakpoint here, and let's just run this. And, all right, of course, it will ask for some input. So we do like this, and then this, and yeah, shame on Windows Defender. Yeah, it's calling this program suspicious. So now we got an exception already here. Exception, single step, and let's see, it's step into and step over, yes. So we are now just at this call, and we can, oh, it looks here like, all right, we didn't look too much into this before, but it looks like the input I gave was transformed a little bit. So it looks like this the license ID was repeated. So maybe it's like repeating to pad out or something. We didn't look too much into that part of the code. And it looks like the license key or something has been modified. Maybe it's like subtracting stuff from the values or something. Yeah, so it's a good question what Windows finds, Windows Defender finds suspicious. I mean, it could be the like switching between 32 and 64-bit. It could be like this I guess like some kind of like self-modifying code or something, or it just happens to share some behavior with some known stuff. Anyway, we're now about to call into this seemingly bogus code. Right here. Oh yeah, the virtual protect is probably a bit fishy as well. Like that's so there's like several similarities between this and malicious code. Yeah. Anyway, let me just the instruction pointer is B3. Yeah, so this is completely incorrect. Like here it has disassembled it unaligned. Like it has disassembled from B2 here, but the instruction pointer is actually B3. So it doesn't make sense. But let's see what happens if when we try to execute this. Some kind of access violation, and we should. Can I get it to jump into the? So what I want to do now is I actually want to debug into the exception handler. I wonder if we can do that. Oh, cancel. Maybe that's a bit tricky. Oh, by the way, here you can see it. Okay, actually you can't really see because of the size, but now you can see that the permissions here are changed to like execute, read, and write for the whole program. So that was indeed what the virtual protect call was doing. So I want to set this up in such a way that I can see what's really going on. I wonder how I can do that in a nice way. So here we can look at our exception handlers. We can even go to this follow handler. Okay, here is our exception handler. Can I? Oh, now okay. Now I could set if I set the breakpoint in the exception handler and just continue, we get here, and I wonder if this is gonna be correct. So we have this stack here. Or maybe this is actually now not correct anymore. I'm a bit... So this is something I haven't really done that much. So yeah, I'm not like I'm definitely not in like comfortable territory right now. Here we see the comparison against this. So this EBX, follow in dump. So it looks like C5 or like C0000005, which is neither of these. So it's probably just gonna fail the whole thing. And then, all right, now we are in like libc or something. So yeah, this is yeah, not gonna work at all, I guess. Need to find a better way of handling this. Yeah. So what's a good way? We need to find like a good way of approaching this. Maybe we could try to doing it a bit statically again. But I mean, at least so far, it's like looking like it's doing what like the things we looked at so far seems correct. So maybe we could just quickly look at this again. What's going on here with the so like push F and pop F is just like modify. It's like that's like pushing all the registers and stuff, I think. Push E flags registers into the stack. Yeah. Right. So this is exactly what we're doing. Like write E flags, and then we're ORing this back. Oh. I'm just gonna. I think this is what kind of like drives the whole thing. I just want to see what this is actually doing. So which can I get the flags register here? Mask trap flag single step. Okay, so that is what we're doing. A trap flag permits operation of a processor in single step mode. When a system is instructed, it will execute one instruction and then stop the contents of registers. Okay, so we are like switching to this like single step mode. I guess. Which that actually made sense, because that was why we got the break, like one instruction before I actually had put the breakpoint. So that makes sense. Oh, and then okay, so is the right, and then this is just something that will be executed on every instruction then, I guess. Okay, but then we should be able to like do this a bit. We should be able to do this statically, I guess. So let's see. So let's just look at what happens first time we step into this. So it will call into this bogus function, the verify license, and this should go into this mode here, where this thing should not be set, I think. So this will not be executed. This thing will be executed, and this will only do stuff if we are inside this range. Are we? I think so, right? Because here we have this verify license thing, and this is, yes, it's between the start marker and the end marker. Okay, so this stuff will execute at the current instruction pointer, where it will copy the current the bytes currently at the instruction pointer. It will copy to this temporary array. Okay, so maybe this is basically just like whenever we execute an instruction, it will save those 15 bytes, because I think the maximum length of an instruction in x86 is 15 bytes, if I'm not mistaken. So by copying the following 15 bytes, we know that if we only work with like 15 bytes, we know that we will always capture the one instruction. This is probably like going one instruction at a time doing this. So we store the original contents. What probably happens then is that we kind of like decrypt the instructions or the instruction, and then we can execute the next thing. So this would be like restore encrypted code, and this would be like decrypt code. And then we will have to figure out what this thing here does, but we'll get to that later. That's probably related to doing like function calls or something, like to library functions or something like that. So we call this like maybe decrypt instruction, and this is like the encrypted, or like, I don't know, save the code or something. So now we'll just have to figure, so if we can figure out what this encryption or decryption function looks like, we should be able to just implement this in a like a small piece of code to just manually decrypt all the code. And then maybe like load that into IDA again and like disassemble it. So this will take 40 bytes here, which contains a bunch of interesting. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it will copy all of this. Whoop. No, this looks incorrectly aligned. This should probably be okay, look, it's just one. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. 10. Okay, so this is some kind of table with offsets to function. We can just we should name these so that we know that they are somehow related to each other. We don't know what they do yet, but so this is some kind of like function table 1. Okay, that's something. Oh. Why is this? Okay, for some reason it didn't really like that, but anyway. So we're copying this into this array, which is here. Func table copy. And then, oh, so is it... Okay, so we have this table of 10 different functions, and then we look at the offset of our instruction pointer modulo 10. I guess. And then what we get the offset, we divide it by 10 and multiply it, so we can like round down to the nearest 10. And then what do we do with this? We store the original one here. Oh, sorry, then we subtract. All right, and this is going upwards. And here we're indexing into this function table based on this. Okay. So this is just doing a bunch of arithmetic. And is this also like... So what about logging IEP plus the decoded instruction each time the exception handler is called and then disassemble? Yes, that is a very good idea. And I think that would be a good dynamic approach to do this. So now we just need to, in that case, we just need a good way of like tracing this. I wonder if... So this is like on Linux, I definitely kind of know how to do this, but I wonder if we can do... oh, now I... So let's try to go to this exception handler. First of all, if we just run this, yeah, so the problem is we can't really do this, I guess, properly inside. Or maybe we can actually. Or maybe not. BB3. Yeah. Yeah, this is really, of course, not really working well with the debugger, since like the mechanism itself is like using the single step function. So for some reason we never like, you see the instruction pointer stays here at like BB3. So we would need some kind of tracing thing. What would be a good tool for that on... What's this? There's this tool on which should be on both Windows and Linux. You can do this like Windows trace execution. I wonder if we could do it with Windbg. So I am not very experienced with Windbg, but I wonder if we could use that. Let's try that first. Let's close this program here. Start debugging, launch executable. Right, so where was the address of this thing? I guess here would be a good point. Can we just put this like this? Okay. Windbg set breakpoint. Is it just pp? This is how little I know about Windbg, but maybe that's how it works. It looks like something turned red. So if we like continue, debug is running, enter this, enter that. So now it's at F like 39. Okay, so we will have the same behavior here, of course. But could we just use Windbg trace instructions? I don't think this is what we're looking for. So let's. I will try the like static way a little bit more first, and then we can look at this again. But it is a good technique in general. Just try to trace the instructions being executed and try to disassemble that. And then of course this it might be the case that there are a lot of branches and stuff, and that technique will of course only trace the branches taken. So you might have to do this multiple times or something, or just to use it to get a good understanding of what's going on. Let's look at these 10 different functions that we were looking at. Oh, right. Okay. So this is some kind of like XOR function. And this, okay, so these 10 different functions, they represent small operations. So we have this like XOR add, rotate and add, XOR with the address, like subtract the address, and then we have like add the address. And then what we have rotate and not. And this is a XOR and not. And then we have an XOR with the Oh. This isn't like the XOR of the not of the address. It's not really important exactly what it's doing. It's just that we have 10 different functions with like small computations. So this is some kind of like roll XOR roar not thing. Not super important. But at least we know that these all follow the same format. They take an address and they kind of perform some kind of like decryption or like computation on that location. So I guess this is why we have this modulo thing as well. So this is like offset mod 10, and this would be the offset round 10. And this would be the next. So this is counting down here. And this thing here is doing the decryption. And this would be the pointer. No. So starting pointer plus 10 times this divided, yes. So that would be a pointer. So let's look at this is like extracting some kind of value, modulo 10. Okay, so this is like the function index based on this pointer. Then then it takes this this will be the function pointer. I'm not exactly sure what's going on here, but wait, will it call this thing like recursively? Okay, this is getting pretty messy. But is it ever calling this function in the function pointer? So function pointer. Let's see. Wait, here's some code that's not. Some tricky. Yeah, some more people showing up in the chat. Hello, Jesper. For some reason, this part of the function was not included in the decompilation. So yeah, not exactly sure what's going on here. It would be nice if we could just like emulate this code, which I guess maybe we could. So that would be another idea, to like just like call into this function, because we could just set up, or like just emulate some part of this code. So let's go back to this structured. Yes. But anyway, after this has been called, we have this part going on as well, which will take, so this is some counter. Which will take so this will actually perform the modification of the code. So these are those 15 bytes which will be modified. But this makes me wonder, what is this part actually even doing? But let's look at that for a moment. So here we're actually like decrypt 1 byte, and this is a pointer, and then we're calling into this pointer. Oh, okay, and here we use the function table. Right, and we extract, so this is the like decrypt operation, and this will actually return one of these functions. So we should actually change the type of this. This thing right. Okay, so I think that what this is doing is like it's setting up this table of different functions, and then I think it's like shuffling them up or something. Yeah, so this is probably what's going on. So this is like set up function table. So for every instruction, this is like the hypothesis so far. For every instruction, it will take this table of 10 different functions and make a copy of this based on the offset where this instruction that we're going to decrypt is located. It will like shuffle this table, and then for every byte in this instruction, it will call one of these one of these 10 functions, which will perform one of these very basic operations on this byte, and this will be then used to decrypt the code. Here, and then the code is decrypted. So the execution is returned to that code. It will execute, and then there will be the next instruction, which will trap into the exception handler here again, which will then restore the previous instruction that was executed. So it will like re-encrypt the previous instruction, and it will decrypt the next instruction, and then let that execute. And then this will just go on and on and on. And it will perform this thing, or like it will execute this license verification function. So this is what all this encrypted code here is for. Now, another question is what this huge chunk of data here is for. I don't know, but that's also something. But anyway, that's my understanding of this program so far. I think this would be a good time to actually take a break from this. So I'm just gonna write down some notes here. Let's just go back to where this is. So here, we are setting up the exception handler, and then here we are setting the single step mode, and then call this thing here, and then in the handler this handler will restore previous encrypted instruction, decrypt next instruction, and this it will do by create copy of this 10 function table, shuffle the copy based on the instruction address and maybe the values, something, we don't know, and then decrypt the next 15 bytes, which is the maximum number of bytes in a x86 instruction, and then return control to execute this the decrypted instruction. So this is what I think is going on. And basically then to solve this, you could go for either for example, if I figure out how this decryption function works, I could just implement this in like Python and just decrypt the whole code blob, and then just load this into IDA and something and continue the analysis. Or we could run this in some kind of like tracing debugger to just say could list all the instructions. We could dump all the instructions executed. Unfortunately, I don't currently know of like a good way, or like I'm not familiar, I haven't done that in a very long time on Windows, so I don't even remember what tools I would use for that. I think there's some really nice things to use, but I'm not comfortable with that, so I would have to maybe like look that up and like play around with it a little bit. But yeah, so this is basically how far I got in about 2 hours and 15 minutes or something. But I should probably do like a part 2 of this and finish this, because this looks really interesting. So the next step would be to figure out how to defeat this encryption scheme to decrypt the code. And then, of course, from there, it could be either super simple or like another layer of something horrible. So we don't know that. But yeah. So I don't know. Does anyone have any, I don't know, questions, comments, something? I think I saw the author of the challenge here as well, in the chat at some point at least, Antonio. But yeah, very, very nice challenge so far. And yeah, of course, also my plan is to maybe do more of these streams as well. So if you have like a suggestion for a challenge that could be suitable, feel free to reach out, like write me on Twitter or whatever. And yeah, you know, the usual stuff, subscribe and so on. But yeah, if no one else has any questions or anything, that's it for this time. So thanks for watching, and have a nice evening or whatever time it is where you are.